Okay, moving straight on, this will be more relevant again for our system integrators. And I think it will cover a lot of the questions that were asked just now, but we'll go through them again and I'll try to take my time for this one. So in these tips, we'll go through battery limit management. So especially talking about how to manage the oxygen and hydrogen vents. We'll talk about cabinet integration, what kind of environments you should choose which cabinet in. Tips for water purification and how to supply water to the electrolyzers. And we'll present very shortly how systems are monitored and controlled in general when you're putting them together. And we'll be going through some references in the industrial standards to talk about where can you look if you're wondering about, if you don't know something, because industrial standards are available and make a very good resource for finding out how to get the systems running in a accepted way. So, right, our electrolyzers, as we said before, there is a transfer of responsibility when we supply the electrolyzer to you and then you just install it or deploy it in a customer site or system. So in general, we have these tips also written down in the owner's manuals for the EL 2.1, for example, but they will be more well described for the EL 4.0. In general, though, operators and system integrators need to be aware of the following. Do not use the system in an explosive atmosphere. This means that not just that you can't use a system in an ATEX environment, but it must be excluded, and you must make sure that there is no possibility of explosive atmospheres forming. So there needs to be some technical installation around the system to enable either very good ventilation or hydrogen detection that can trigger safety functions to occur. We are not responsible for if you're using the systems improperly. So a lot of people are asking us sometimes about oxygen. So this is one of those points. We are currently making hydrogen generators, and you cannot technically use the oxygen. But if you did, it wouldn't be on our end where we're assuming the responsibility for this. So the systems should not be used outside the environment, operating conditions. We should not supply any wrong inputs or input pressures to the systems, and ensure that the system is mounted properly. Power supply, also important, including getting the right cable sizings and everything. Additional safety tips. These are not really tips, they're kind of self-explanatory. Like, don't put high pressure equipment behind the systems. Do not pressurize the outlets higher than the maximum outlet pressures. Don't supply water to the systems that are outside of the operating specs. And don't supply with too much pressure the water either. Never block the hydrogen purge line, and don't obstruct the oxygen vent line. The systems need to be able to release the gas that's inside of them. So battery limit management. Why battery limits? It's just a fancy way of saying interfaces, really. But in general, operating temperatures, the differences between the air-cooled and liquid-cooled electrolyzers, and how we can optimize heating and cooling, these kind of questions will be answered at a later presentation, I think when we're talking about the cluster. For now, let's look at the battery limits from the individual electrolyzers and what you have to do in order to get systems combined into bigger electrolyzer installations. So having several electrolyzers to get deployed kind of changes the way that people focus on the battery limits. If we think back about yesterday, about the safety training course, we should not just consider what normally comes through the line, but what could possibly come through the line in order to properly anticipate and check for the system failures. Ooh. So understanding the flows and the media inside each line across the full spectrum of operating conditions and even the failure modes becomes much more important to avoid cascading failures of the system. If one electrolyzer breaks, you should make sure that other electrolyzers don't break. Good news is we definitely thought about those ones. Having the systems be stackable and modular is extremely important for us to say, okay, these systems cannot be breaking each other. We have to make sure that the systems are operating in safe conditions when they're connected together. Our design principles are very clear in this regard. So we were aware of the AAAs, of avoiding the hazards in the first place, and then anticipating the problems and making sure that we adopt best practices for the system management. So we'll go through it in order, kind of, as to what you have to consider, but we'll be looking at power management, what kind of input cables and what kind of considerations need to be done there. And we'll make our way all the way down to the input water pressures and the systems and how we supply water to them. So power input. This is specifically for the AC/DC version. So where you have not the DC power supply to the system, but AC. So don't ignore appropriately sizing the cables for any installation. It's a very dangerous thing to supply power to systems with insufficient wiring. So we've seen, systems get where the input power cable is starting to melt just because someone wanted to plug it into a wall, and then the whole cabinet was getting through the one socket that wasn't rated properly. So this should be avoided, and you should make sure that this doesn't happen on your sites. System integrators are responsible to follow and comply with local rules and regulations for any system deployment there. The AC version of the electrolyzer is single phase, and when you're consuming the maximum amount of power, about 13 amps can be absorbed through machine. So it's important to size the power lines properly. And as soon as you're deploying more than 3 electrolyzers, we recommend that you use a 3-phase power input and then split the lines and distribute it for each electrolyzer. This helps quite a bit balance the load, but of course, continue to keep in mind that if you have some peripherals that you also connect to the system, that this can unbalance your 3 phases. So make sure that you are looking at the load on each phase and balance it accordingly to keep the power supply stable. Vent lines. Overall, when it comes to our devices, don't place the devices in a sealed or unventilated room. So some people will say, but I've put it on a mountain. I need it to be sealed or unventilated for now. Okay, we completely understand, but there needs to be risk reductions in place about how to, for example, dissipate any accumulated hydrogen should there be a leakage from either the systems or from an external part of the units. Don't place any flammable materials in the proximity device. So in general, don't put sources of potential ignition sources nearby. Don't smoke nearby, especially near the vent lines. And yeah, in general, keep the lines clear of debris and obstruction. So this goes for any line. It is your responsibility to implement safety areas around the vent outlets. We're going to get to them, what they look like in a second. But essentially, the system, while it's running, will release oxygen from the oxygen vent. There will be some percentage of hydrogen inside. And from the hydrogen vent line, there will be periodic purges or hydrogen releases outside the system, which can come out with a higher pressure. And this needs to also go to a safe location where you don't have any sort of risk of ignition nearby. The vent lines need to be grounded, of course, and make sure that there's no static buildup that can happen inside of them. so that you are avoiding the risk of ignition inside. But as Danny stated yesterday, you have to decide whether you want to make sure that the lines are protected from explosion, or whether or not you can just say, okay, even if a deflagration happens, the line's not going to break. So you need to have some sort of pressure rated lines, even if there's no pressure inside of it normally. Oxygen vent management. So every electrolyzer at 100% production rate produces around 250 normal liters an hour of oxygen and condensing water inside. So there's quite a lot of water vapor inside our vent. And this accumulates around 25 milliliters an hour of water. This depends on the ambient conditions. So if you are in winter, it'll cause more water to accumulate than in the summer. This water needs to be managed. If you have it remain in a line, this will cause a lot of noise, probably bubbling through the lines. And it's overall a pretty unsightly work if you are having the water that get trapped in the line. And it's not good engineering practices to have liquid water remain in these type of process lines. So draining it out is just another way of hazard reduction in order to, for example, reduce the risk of freezing inside the lines or causing some sort of blockage. So generally, the water inside the line can create this stagnation or the stagnated sections. And so we generally advise people to have a collection line which is tilted slightly towards a water trap, and make sure that the flow speeds inside the lines are kept below 25 meters per second. This is just general rule of thumb. Outlets, again, need to be protected from blockages. Placing specific design vent lines could also be a good solution to exhaust the gases. So if you look in the picture on the bottom right, you can see what vent lines look like in some industrial sites. And here what would happen is if the systems were on and it would be cold outside, you'd see a lot of vapor appearing on the top and in the bottom of the lines. And so you then, of course, also have to keep a lookout that there's no bugs nesting inside or any conditions that can start fouling up the line or something like this. But in general, these type of lines, when they're so large, actually become quite easy to manage, and also easier to predict the size of the safety area around them. Later on in this topic, we'll be covering some industrial standards that you can use to refer back to what is the correct vent outlet look like. So now hydrogen vent. Now it used to be called the hydrogen purge line for us on the EL 2.1. We've been told it should be the hydrogen vent line. And some people even say this should be called just the hydrogen dump. I prefer hydrogen vent. So while having several electrolyzers in parallel, the purge lines cannot be sized according to good practices easily like the vent line, because the pressure differential between the stack and the atmosphere make a very, very fast initial flow speed. So we can kind of start by ignoring the 25 meters per second because you're going to get very fast flows. But then you should start considering, materials, ignition sources, and make sure that you have the correct sort of implementation in place to manage the little liquid that will come out with each hydrogen vent or hydrogen dump. So if you can see here on the top right of the presentation, you'll see a collection line with several inputs. And so this is kind of the idea that a lot of people are doing in order to also collect the purge. So if you have many cabinets sitting side by side, you could put it into a single purge line, and there's a single water trap or manual release valve at the end of it, at the bottom section, to also make sure that the water doesn't get trapped inside the line. For liquid water inside steel pipes doesn't seem like a problem, but it can actually crack lines and cause leakages. So it should be avoided if it freezes. Exterior management of the lines should be exactly like the vent line. They have the similar specifications and industrial standards referring to them. One thing to make sure, keep the lines separated. Do not put the oxygen and hydrogen vent line right next to each other, even though it looks nice. It's better to keep them far apart. And if you remember and look back at yesterday's safety talks, hydrogen doesn't just go straight up, but it spreads. Okay. So hydrogen outlets. So this is the output of the electrolyzer. This between the EL 2.1 and the 4.0 remains unchanged actually. First of all, ensure that your material of the lines is appropriate for hydrogen service. So, we generally use these stainless steel tubes from SS316L, which has a good hydrogen embrittlement resistance, and size the lines according to good practices. So once you're combining many electrolyzers together, the lines should get bigger. If you look here on the side on the picture, this is actually something that we're currently building ourselves. We're putting more test stations in, and we can see that the lines on the back of the cabinet enclosure are being managed quite well, with a slight decline there as well. So depending on the use of the produced hydrogen, please consider using buffer tanks. So if you're constantly using the hydrogen in industrial processes or something like this, a lot of people will want to have a constant flow coming into their use case. But if something is, for example, a boiler is turning on and off throughout the use of the day, then you want to avoid cycling the electrolyzer constantly as any electrochemical system. So putting a properly sized buffer tank and ensuring that the good system control is established in order to minimize the number of ramp ups and ramp downs will be very important. Furthermore, the pressure relief device between the systems is recommended on the hydrogen output line. So in order to, for example, comply with the ISO 22734, implementing safety relief valves on the output of the electrolyzers is actually quite important in order to ensure that should everything fail, that the systems do not get overpressured. Furthermore, when you're designing the systems, consider extra connections. Where are you going to bleed hydrogen from? Should you, want to empty a tank or something like this? Do you need to worry about commissioning the system? Is there air inside at the time when you want to start putting in hydrogen? Do you want to look at and monitor the hydrogen purity at all times? These kind of questions you should ask yourself before you start assembling the system. But in general, if you have questions about system setup and about your specific deployments, whenever you have questions, feel free to reach out to the support team, and we'll be able to help you, and we'll be able to learn together. So safety considerations, we've already talked about it a little bit, but on the electrolyzer, there is a dry contact with the main connector on the bottom and the repeater on the top. So you can actually use this to daisy chain a bunch of electrolyzers together so that a single input from a dry contact can trigger a safety shutdown. What does this actually entail? Is this an actual safety device? No, but it does allow you to essentially have an alarm level trigger. A lot of hydrogen sensors and fixed installations will have a relay built into the hydrogen sensor or detector that can trigger some preliminary actions. For example, if you have a trigger limit at 200 ppm inside the room, this could mean that, okay, at 200 ppm, shut down the hydrogen production, at 1000 ppm, cut the power and make sure that everything stays safe. These type of things are quite common. Furthermore, when you're designing your room and deploying the systems, make sure that you don't have any space where hydrogen can accumulate. If you do have some dead spaces, it's best to provide some air recirculation inside a closed room. And if it's not a closed room, then it's better to place hydrogen sensors directly in the stagnation points to be able to figure out if hydrogen starts accumulating there. And hydrogen detection, as well as any part of the system safety generally is still important to be implemented according to local regulations. So all the information that we're giving you here, you have to actually double check in a way when you are installing the system. Depending on where you are, we can help you more or less with the navigating the recommendations and the generally accepted best practices. So for cooling, how do you make sure the system stays cool? The heat dissipation should be considered, especially when you start putting more electrolyzers together. So at 45 degrees Celsius, this is our maximum ambient operating temperature. The fan is going to be running quite a lot. And if we don't have space at the back of the electrolyzer, what will happen is the cooling power will stop, will decrease. And therefore, we generally insist on at least 30 centimeters of space behind the electrolyzer in order to dissipate the heat properly. But there are some ways to decrease the space if you are looking at, implementing the system in cabinets or or containers where space might be at a premium. But then these solutions all need to be tested and verified specifically for each of the applications that you're doing. So a lot of times when this kind of questions come up for limited space environments, often the liquid cooled version might be easier to implement for this reason. So for closed containers, heat dissipation to be taken into account is at the end of life around 1,150 watts. But this is, the worst case scenario essentially. So for the water feed lines, the supply calculation can be done quite easily. In general, we have standard configurations for our systems where we allow the refilling to happen in, a way that is, sorry, I don't know the word, that is based on our water tank 2.1 essentially. So the water supply from our WT 2.1 allows a quite easy filling and refilling of the systems. But if you are trying to avoid the water tank and you want to put your own water system in place, then the sizing and the essential following best practices to keep the pressure in the lines in a good way will help you control your systems. From the support team, it's quite common that we actually intervene on customer sites when they ask for help in order to fine-tune their setup in order to get the best refilling performance. Consider system maintenance during the system design. Always make sure that you understand that how you can flush a line or how you can clean a line should there be any dirt that goes inside. And we generally recommend that you monitor the quality of the water input at all times, just to make sure that you're not bringing any bad or high conductivity liquid inside the electrolyzers. So what do you want to do with the cabinet? How do you make sure that you get the system in the right place? Well, I mean, it depends on your environment. It depends on the safety equipment that you want to use and the kind of safety concept that you're following. It depends also on how you want to manage the bulkheads, if you want to keep maintenance topics in mind or not. But for sure, leave space for piping and stuff like this. But also, how you want to do the cable management. So I made this handy flowchart about cabinet selection. And essentially, there is 3 major types of cabinets that are pretty commonly used for our systems. On the left, we've got the indoor cabinets, which are usually simple ventilator rack mounts, or liquid cooled racks, which is just the 19-inch IT infrastructure where you are connecting the systems. On the other side, we have the climate controlled cabinets, usually with an IP rating inside. Containerized solutions, it depends exactly on how you are using your container. If your container is temperature controlled or not, will depend on how you can implement the systems. Now, the question also is, do you really need a cabinet No, you can run your systems on, homemade welded metal systems, or you can put it on your IKEA shelves if you really feel like it. But in general, the integration for these 19-inch racks is the easiest, and so this is what we recommend. So if you were to follow this flowchart, you can see that we can go through a sample here, and let's say we wanted to deploy an indoor cabinet. And this time we don't want to be compliant to we don't need to be compliant to the ISO rating. So actually we see immediately that we can basically use a cabinet with an IP rating of less than 20 or 20 if you really wanted to. In the past, IP20 rated cabinets is the usual selection for residential applications. Why? It's because it's the cheapest. In the end, when you're putting the money into a hydrogen system, you don't want to be spending a lot of money on getting the systems integrated into an IT rack. So ideally, the best thing you can do is to get with the less than IP20 IP rating, a simple cabinet that has these vented front and back doors, and they look really nice. So the main considerations to be done here is I've given some hints as to what safety systems or safety considerations have to be done. So on the 19-inch rack, which is completely ventilated, it's basically like integrating the systems on top of a table. You need to make sure that you have the independent safety system around the units in order to perform any sort of emergency functions like technical ventilation or hydrogen detection. But this is usual for any sort of integration into a space or any sort of environment. But if you are enclosing the cabinets in something like IP34s or even outdoors where you might have some sort of restriction in terms of the airflow going through the system because of temperature demands or something like this, then you immediately have to go to this active temperature control. Maybe air conditioning or heater has to be inside. And then if you have this closed unit, you cannot be blowing air through it the whole time, which is another one of the selections you can do. But you need this active hydrogen leak detection directly in the cabinet. And you may need to check for further risk management measures, which may be required in this way. So water input. The water input requirements for all of our systems remains the same. The conductivity of the water, the air water input needs to be below 20 microsiemens per centimeter. But where do you start with, giving this kind of water to the electrolyzers? So first, if you want to do it very, very well, you can get a water sample from the installation site to help you determine the specifications from the RO. A lot of times, if you wanted to understand the maintenance cycle of your units and the installations, having a water sample be done before can really help you size the water purification system that you're actually deploying. Furthermore, if you actually check for carbon dioxide contamination in the tap water, this can really help you find more problems because the dissolved CO2 is generally not filtered by typical water purification systems. So just as a side note, if you don't know what the CO2, but you are using a water tank 2.1, this will likely actually help you deploy the systems and alleviate the problems of CO2, because having this open tank that's unpressurized allows this CO2 that's dissolved in the water or trapped inside the water that comes out of the tap to slowly release by itself. And so this can actually help you get rid of some of the contaminant CO2 inside water. Ensure that you set up and prepare regular maintenance cycles for your water purification systems. This is one of the things that you really have to keep track of, because if you start putting bad conductivity water inside the systems, the efficiency of the system will degrade very, very quickly, and you will need to swap the electrolyte fast. Another way is the water tank 2.1 stops you from having the need for constant water supply. So if you wanted to, for example, make sure that you can have continuous hydrogen production, but you're not so sure that you have the good water conductivity at all times, then using a water tank 2.1 helps you make sure that you have the correct connectivity coming into the system, and also gives you some leeway if in case you need to perform maintenance on your water purification system. So what happens when there were some questions yesterday that came up as well about this topic, so I added them here. What happens when bad water quality is supplied to the electrolyzers? And I think the main part of the question was about if the AEM membrane will be broken by this. And in general, of course, you have to worry about contaminants inside the water. But the main degradation effect that we see when there's bad quality water that comes in is from the electrolyte itself. So the KOH solution will then degrade quite fast, and this can cause the system to have some active sites get blocked, and should be avoided. But the system will not break immediately just because you put some bad water inside. Clean water input must be supplied using a pressurized water input line. So when you're supplying water to the electrolyzer, and several electrolyzers want to refill at the same time, the water inlet pressure will drop, and then our electrolyzers will stop trying to fill again. So what we generally advise our end users and system integrators to do is to integrate an accumulator tank inside the line, directly behind the pump or something like this that supplies the pressure to the electrolyzers. Using an accumulator tank is kind of similar to what people do in hot water systems for heating. And this is where essentially there's a bladder that gets filled up with pressure, and you can regulate it so that the water, when pressure on the line drops because another valve opens, the accumulator will essentially provide that extra pressure to be supplying more water to more electrolyzers at the same time. So if you are looking at implementing your own water supply system, there's commercial, there's many different commercial water supply systems available, but also you can make your own from your own clean water tank. So now we're getting forward to the communication of the system. How do you communicate with all these electrolyzers, and how do you make sure that it keeps running? Well, first of all, every Enapter system comes standard with the Enapter management system, the EMS. This allows you to connect your devices to Wi-Fi, and you can from there you can control and monitor all the device parameters inside the system. And you can see and integrate even other devices from external or third-party systems like battery inverters and any sort of Modbus communication device. You can integrate them all into the EMS, and you can monitor your entire energy system via the one interface. More information from that will be given also later, and I think tomorrow there's a specific section for this. We also have, each electrolyzer also has a Modbus TCP IP port. So for this, if you wanted to, generally use it for some sort of PLC control or something like this, you can connect all the electrolyzers in a row directly to a PLC or to a network switch, and then manage the systems from there. Now with the dryer control network, which is here shown in the top right there, this kind of is this machine-to-machine mesh network that allows also the dryer to be integrated with this Modbus control and continue to be controlled and monitored even with less Ethernet cables. So a little bit more about this is there's some links to the handbook. So when we're giving out these presentations, you can follow them here directly to see how the units are supposed to be controlled via Modbus, via web GUI, or via the dryer control network. And then here we have a small introduction about how to use the web interface.
Enapter provides modular hardware and software solution for building energy management system. Enapter Cloud is internet-based monitoring and control user interface for all energy system devices. But what if there is no possibility to connect the electrolyzer to the internet. Our latest 1.6.0 update of Electrolyzer firmware provides convenient web graphical user interface. It can be easily accessed with your favorite web browser over Ethernet connection to your local area network or just a laptop. First, connect the electrolyzer to your local area network or laptop with Ethernet cable. Please note that by default, the HTTP client is enabled on the electrolyzer. Most home or office networks have the HTTP server. If you have your devices automatically connected using Wi-Fi or Ethernet, then you should not worry about the HTTP server. Most likely, you already have it. But if you connect your electrolyzer directly to the laptop, you need to make the HTTP server running. On the Mac, use the Internet sharing option, and for Windows PC, TFTPD64 free app. Access to the app GUI is protected by the electrolyzer's UCMID and PIN code. The label is located on the back panel. Life hack: if you don't have access to the backside of the electrolyzer, scan QR code on the front panel with your mobile phone camera or any QR code reader application. Next step is to log in. Open your favorite browser and enter the hostname of your electrolyzer. Highlighted part is the UCMID. Fill the hostname with your UCMID and press Enter. The authentication page will open. Enter here the UCMID and PIN code and press the login button. Web interface has a simple single-page layout. It is intuitive and fast. On the production metric bar, you are able to monitor the current hydrogen production rate. In case the electrolyzer has some warning or errors, you will see them on the advanced bar. Execution of commands such as start, stop, and locate, and configuration of your device is available at the main configuration bar below. The indicators of the left panel copy states of the device LED lights. Oversee the full system status and telemetry using the monitoring bar on the right side. Maintenance tasks such as first-time electrolyte filling and electrolyte replacement becomes more intuitive and easy with helpful wizards, even without internet connection. Finally, one of the biggest advantages of the web interface is built-in help with Modbus registers.
Electrolyzer web interface does not keep historical data. In case you need it, connect your device to Enapter Cloud. You will find more information on how to use web interface in the Enapter handbook. I left the link in the video description. Hope you enjoyed this tutorial. In case you have any question, leave them in the comments below, and we might cover them in the next videos. Thanks for watching. Bye bye!
Right, that was brilliant. Whoa. Right. So in the end, this basically gets towards the end of the integration tips. But this is just another opportunity for me to remind everybody that we are here to help. So we routinely help our end users and system integrators navigate their way to system commissioning. So if you have any further need for assistance or further explanations about standards, codes, regulations, how our systems are working, how to communicate with them, just reach out and we'll definitely be able to help you. We're trying to make it as easy as possible to figure out how things work. And there's a lot of information available, not just from the support, but also from each other with the Enapter Energy Club. I think more information will be given for that later as well. But in general, contact us at support@enapter.com or write us on the Enapter Energy Club forum where you can exchange sort of ideas. This is just a bit of a background information on what's the standard, what's the code, what's the regulation. But essentially, standards are technical definitions and guidelines that help and that make designers and manufacturers know how to build a system that's similar to others. This is generally considered voluntary because they're guidelines and set by industry and not enforceable by law. but a lot of times regulations will refer back to standards and using them the right way. For codes, this is like a set of regulations, and regulation is just a simple rule or process details as to how certain things are done. This is something that you have to follow. So if there are regulations in your local area about how to deploy hydrogen systems, then this is something to look into. Resources for this are all over the place. I recommend, if you're looking into it and you kind of knew about it, looking into the standards and information that's on the screen now. We have the ISO 22734. We already covered this quite a bit today. But then there's also quite interesting standards from ASME, which goes about hydrogen piping and pipelines. Why do we like it so much? I really like the standard a lot, ASME B31.12, because it is written in a way that really helps you understand why certain choices are being made, rather than just telling you that these things have to be figured out in this way. So from my point of view, I really quite enjoyed working with the B31.12 during our design processes and considerations for material selections and pipelines and stuff like this. NASA safety standards are this is the gold standard of looking up hydrogen and oxygen hazards essentially. And then for vent systems, something that Danny brought up as well, and that I've alluded to a couple of times already today. The CGA G5.5 or the API 521, as well as the IGA documents that are on the screen here, really quite helpful to figure out what can be done for vent line exits and what kind of shape and distances you would have to consider. A lot of times these standards should be taken a little bit with a grain of salt, because the scale of the systems that are being described are talking about vent stacks with kilograms a second being released, which is not exactly what we're doing, but the general rule of the general applications and the deployment measures stay the same. And then if you are in Germany, I really highly recommend, or you just speak German, I highly recommend that you look up the explosion protection rules from the Berufsgenossenschaft, from the Society of Chemical and Natural Resources in Germany. This set of rules and essentially code for how work safety should be done is really, really helpful in trying to determine what type of safety systems would be good to deploy around electrolyzer hydrogen production systems. So this is a very nice resource to refer back to. Danny in the last presentations yesterday also referred to the NFPA 22, which is just the American equivalent of this, I think. Furthermore, depending on where you are at, both the FCHJU and FCHEA are really good resources that are really pushing ahead into trying to define and provide clear policy targets to help system deployment. Personally, I think this is one of the most important things actually for us, as users of hydrogen trying to deploy the systems. Avoiding and eliminating the gray zones and essentially making clear guidelines as to what you need to do in order to deploy systems is, I think, super important. So this is kind of a collaborative effort between the industry, government, suppliers and users. And the best thing that we can do is continuously give each other feedback as to what was working and what wasn't working in terms of system deployments. And then again, for people that may have not been there yesterday, there's the highlaw.eu website. This was a project from the FCHJU in Europe that talk about the set of regulations in place for hydrogen deployments across Europe. Yeah, and that brings us to the end of our integration tips presentation. And we'll take 1 minute to quickly review the questions, and then I'll be able to start answering them.
Super, thank you very much, Max. While you're going through them, We saw a couple Joes asking questions, so still a very popular name today. Don't be shy, and feel free to right-click on your video and you can rename yourself.
Okay, so I guess I will start somewhere near the top. What happens if the water pressure is too low on the input line? What will happen is actually the electrolyzer will not refill. It's not a big problem. So the minimum, we state that the input pressure should be between 1 and 4 bar. If you, for example, have only 0.8 bar possible to be supplied to the electrolyzers, reach out to support and maybe we can get something sorted for you. Other types of water traps also suitable for the hydrogen purge? Yes. So yes, absolutely. There's a bunch of water traps that we have on the Enapter Club. So if you look here at the update on water purification systems here as well, there will be a resource on different water purification systems that you could have and deploy. But also we have the same sort of resources for water traps and for other equipment in or around our hydrogen production systems. Generally, when you are looking at water traps for the hydrogen purge, I think this question was asked by Niels de Smet, a good question again. You have to remember, look at material compatibility and look at the pressures that are possible to be created. So each water trap will have a pressure rating, and you don't want to be exceeding that pressure. In the oxygen vent line, we have atmospheric pressures and just the oxygen environment, which is a lot easier to handle than the intermittent releases from hydrogen inside the purge line. When you are doing this, it's very important to make sure that you don't have a wrongly sized water trap in the purge, because what can happen then is that hydrogen actually goes through the water trap into the drain, and then you have hydrogen in your drain, and we don't know where that one goes. So in general, it's very important to keep these two separated. For smaller lines, where you have access to them more frequently, it actually is quite common for people to implement a manual drain for the purge, so that you wouldn't always purge it. Most of the time, just the velocity of the purge itself would carry the water out of the system. But with larger collection pipes and stuff like that, either a manual drain valve or a properly sized water trap is the way to go. Sandeep Bosal is asking, instead of a dump, can we vent out the hydrogen in an open environment with taking all safety precautions? Yes, this is the same thing, I think. I don't understand the question. Yeah, yes, you can do this. Please, essentially the dump, or I think maybe you're talking about these specific, are you talking about these specific vent outlets? Then no, you don't have to use these specific ones. You can also make it simpler. There's no regulation that states that you have to make them like this, but in general, you want to make sure that there's IP protection around it. So you don't want bugs to go inside. You don't want water to be able to flow in and potentially block it. Tibor Toft is asking, do we need a back pressure valve downstream of the EL between the EL and downstream buffer to keep pressure on the hydrogen side of the system? Okay, good question, Tibor. No, so essentially our electrolyzers are self-pressurized. So first, before operation, actually, we will pressurize the system just during operation from creating the hydrogen inside. And then once the operating pressure internal of the electrolyzer is reached, we start supplying the hydrogen on the output of the line. So you don't need to regulate the pressure inside the electrolyzer anymore. Dieter Hesse is asking, will have a little depressurized environment have any impact on safety, production rate, and cooling? You mean a low pressure environment in terms of on top of a mountain? No, actually our electrolyzers are very robust in terms of the location of where they can be deployed, because we generally operate on a relative pressure setting. Since our electrolyzer is based on essentially having the anodic side, so where the oxygen is produced, be on atmospheric pressure, and the hydrogen side be pressurized, where you end up deploying the system has very little effect on it. If you have an air-cooled system and you're putting it very, very far on top of a mountain, then of course there will be a difference in the air density, and then the air will not be able to carry as much heat away from your system because you're putting less mass flow through it. So that's something to be considered. You probably have a higher heating demand, a higher cooling demand at that point. But deploying the system into the correct ambient conditions, you know, if you were deploying it, for example, at 25 degrees Celsius and you made sure it always stays there, then you will have very little problems with this. Dr. Hong is asking us, is there a heat dissipation study on the liquid-cooled version because of some parts of the liquid-cooled version are still air-cooled? What is the recommended space behind the liquid-cooled version? Okay, so actually there is you mean the electronic box inside the EL 2.1? Yes, that's still, I think that's still air-cooled, yeah. But there is actually, we don't have a proper definition for the recommended space behind the liquid-cooled version. The point is that actually you can have quite little space behind the electrolyzer itself, but you need to enable the chassis ventilation fan to continue to spin and provide the correct airflow through the system. So if you were to you know, have no space behind the electrolyzer, you would not be able to run the system because the system would go into error from having too little air getting put through it. But yeah, if you have more questions about the liquid-cooled electrolyzer, I think the next presentation will cover this. What happens beyond 45 degrees Celsius ambient? Is there a derating and an inefficiency, auto shut off, or is it out of spec? It should not be installed in those conditions. What will happen is the system will start overheating and then it will shut off. But no damage should be done from this. You should not operate the system in these conditions because you will not be able to have consistent hydrogen production. Catherine Prince is asking, do the electrolyzers have built-in conductivity sensors? Can they provide measurement values of the absolute water conductivity? No, our electrolyzers, they do not measure the input water conductivity, but our electrolyzers are able, we can tell essentially from analyzing telemetry of the system if there's been bad water supplied to the electrolyzer in recent times. Therefore, actually, it's very important that either system integrators take care of the conductivity measurements and monitor these, the values, so that no bad water is supplied to the systems, or to use a water tank module 2.1, where there is a built-in conductivity sensor. And so that way we can be for sure that the systems are not being supplied with bad water. Carlos Enrique Manilo is asking us, additionally to the conductivity, what other parameters are necessary to consider? Hardness, pH, I don't know what that word is, size? So yeah, I mean, hardness and pH, important to consider, yes. When you are looking at the water studies, ideally you should check for CO2, the hardness, the ion content of the systems, and what type of ions there are. Because depending on the contamination of your input water for the water purification system, you may be able to choose, for example, different types of resins that might need less replacement or something like this, or just sizing and knowing the amount of ions that you have to pull out of the water, you'll be able to size a better system with, you know, the maintenance cycle that is appropriate for the installation. What are the specifications for the cooling water? Oh, liquid cooled versions we'll describe later. 1 liter of water a minute. Is this correct? The EL 2.1 data sheet 0.4 liters an hour stated. Oh, no, the input water of the electrolyzer. So when they refill, they consume 1 liter an hour momentarily, but the actual consumption is the same. So we still consume about 400 milliliters per hour of DI water. Sebastian Alvarez is asking us, can dryer control network be established with Ethernet cables or other physical communication between EL and dryer device? No, not at the moment. This is done by the M2M network. Ramando is asking us, can we just use the Modbus controller to integrate all electrolyzers to our general automation. Yes, absolutely. If you have problems with this, reach out to support. We'll be able to help you. What brand of water traps do you recommend? Can you give us a model of water traps and specification? How often must we change the water trap? So in generally, we use these, they're called the ball valve water traps. And essentially what this is, it's a ball connected to a small lever that if the water fills up to a certain height, it actually starts draining the trap by itself. So it's an automatic drain. And if you are using it for the purge line, when you're talking about the common purge, which you want to drain manually, then it's something that you have to see in your installation. Ambient conditions, of course, matter again. So you should check how often you have to drain it by just testing this during the commissioning phase of the system. Enapter communication is one-way or two-way? Stacks could accept commands from external remote. Yes. So it's two-way communication. So you can control the systems using Modbus as well. There's another Joe. Enapter communication. Oh, okay, that was already just answered that. Sorry. Does Enapter plan on aligning with a fuel cell for a complete package? I think this is more of a BD question. Maybe someone from BD wants to jump in from this one. But essentially, my opinion is that we make electrolyzers and that the fuel cell packages is kind of the ball area for our system integrators.
That is fully correct. We are laser focused on producing very efficient, cost-effective, and easy to use electrolyzers, and this is our core aim. But of course, we can provide you with help if you need to find a good fuel cell. We have also made some lists. Maybe a colleague of mine can share them. As you can see below already, a list found in the Enapter Club.
How frequent do you think that the system would require preventative and routine maintenance for the complete system? So our electrolyzers and systems, they all require yearly maintenance. Preventative maintenance, of course, is generally done when it's needed. You can see that we're monitoring the telemetry of all systems. And so in case we see an issue start appearing, or we can identify a certain failure mode and certain parameters, we can actually perform preventative maintenance by reaching out to our system integrators and letting them know about this. But in general, routine maintenance of the system should be done once a year. How you do the rest of the complete system maintenance is again depending absolutely on the the rigor of the installation. So some people will perform some sort of hazard reduction due to the frequency of the maintenance visits from trained professionals. Other people will have more access to the systems and then be able to say, okay, we only do this check once a year, but we have access to the systems and we monitor the hydrogen concentrations at all times, etc. And then there's places where, for example, certain components may have to be replaced on an interval that's based on some sort of local rules and regulations. And this may change literally country from country, even within Europe. So safety relief valves or something like this, you should check your local rules and regulations for this. And it of course depends a little bit on your HAZOP and risk assessment of the installation. Are all the units and components made in Germany? No. At the moment, all the units are assembled in Italy. But the Enapter campus is coming soon, and then they will also be made in Germany. Vian Kumar is asking us, we have noticed that the electrolyzer go to standby as soon as the set pressure is reached. Is there a way to slowly turn down the hydrogen production? Yes, absolutely. Good question. So we can, for example, using the EMS, we can program specific conditions into the system that kind of work like a PID control. So you can approach the set pressure and then start ramping down the electrolyzers before the set pressure is reached. This is especially used quite frequently in installations in industrial applications where you have to deploy the systems into other industrial settings that may or may not need the hydrogen at the time. So yes, really good question. Yes, we can do it. Apollo Technics is asking me, the AC-DC converters are needed for the electrolyzer. Is it possible to just connect it to a DC source? Because converters also generate DC ripple. What ripple are allowed for the electrolyzer? Ooh, good question. I don't know. I'd have to check our DC-DC electrolyzer datasheet. If you email support for this, then we can also get the electronics team to give feedback on this. What is the life of each cells of the stack? It's a good life. It's a great life. After the life, can you replace refurbished cells? Yes, we can do this sometimes. Depends. We want to make sure that the stacks and each cell inside the stack has a good life. And so, the first and most important thing is that, first we make them here at the moment in Pisa. And then when we ship the systems, we actually would like it if we can kind of create the circular economy. So when the systems have reached end of life, please do send them back to Enapter, and we can refurbish them, recycle them, reuse them in the best ways. Okay, I think I've reached the end of the questions. I think we're ahead of time.
Yeah, I think it's a good time to take a breather before jumping into our next topics. I would say let's take a break, and then we can come back at 3:45 to talk about our partners and our partner program and service partner program. So go stretch your legs. You have 6 minutes. I'll put a timer, and then we'll start on the dot at 3:45. Thank you, Max. That was great.
Thank you, everybody.